Good to see you there. Where's me?
Okay. Okay, we can. You ready? Okay. Okay, so let's start with Jay Benton's PhD dissertation defense. He's going to be defending his work on partial satisfaction planning, representation, and solving methods. I normally try to say a couple of things about the student because after this is all downhill, there's a lot of problems. So Jay, I mean, I've been told that women should not be asked how old they are, and you are not supposed to ask a PhD student how long they have been in the program. So you would say that Jay has been around. He is actually in our own bachelor student as well as master's student, and he's been in the program for a while, and he's completed very nice work, I believe. He has several papers. He's given tutorials at IIII. He got 2 Best Paper Awards just this year. He has a planning system
from the same conference?
2 different conferences. And he has a planning system that got a Distinguished Performance Award, and he's also a super collaborative guy. He has works with lots and lots of people. And that sort of brings me to his personality. He's sort of everybody's best friend in the lab, and also probably the department. I think he's the only one that people go to if they have any kind of a problem of any kind, and he's also our social czar. So the few hikes that, we are rotten people, normally don't do hikes, but the few times we did hikes, it's because Jay actually organized them. And then I think I personally, I think apart from just being a student, he's also been a great friend. I mean, I'll really miss having somebody right there who I can make references about Seinfeld and hope that they'll understand. He knows all the Seinfeld episodes, I know all the Seinfeld episodes, and we could just talk in Seinfeld episodes. The rest of the students, unfortunately, are not like that. So I will certainly miss him. So if the committee, in their infinite wisdom, decide to keep him here for some more years, it's fine with me. With that,
can I ask a time-related question?
Yes, sir.
How long had your hair been growing before you had it cut?
15 years, I think.
And you were in grad school all that time?
Since the Earth's crust is still warm.
Oh, I should also mention that this is one of those committees where non-ASU committee members are in a majority. If you count
no,
that
about.
Come on.
I'm still official.
Okay, then we are still ASU majority. So Dave Smith and Min have flown in, and Pat just flew in the other day. But thanks for showing up. The stage is yours.
Thank you all for coming. So I'm going to be talking about partial satisfaction planning. And in order to talk about partial satisfaction planning, I'm first going to just say really quickly what in planning we usually look at. What we usually look at are problems called classical planning problems, where we have an initial state of the world that we're in, so just where everything is in the initial state of the world. We have a set of goals defined by a user, and we have a set of actions also defined by the user that will allow us to get from our initial state of the world to the state containing that whole set of goals. So that's the usual view of planning in terms of just the classical view of planning that often planning researchers look at. Of course, this isn't really a realistic view, and in fact, this is a good example of this. This is our agent Alice. She has 2 goals. One is to have a project done, and another is to take vacation time. But she complains these 2 goals are mutually exclusive, so she can't satisfy these goals. So Alice is like a planner, a classical planner in some sense. She'll come back if you give her goals that you can't solve for all of them. She'll come back and say these are mutually exclusive. I can't find a solution. So that's sort of where partial satisfaction planning comes in. We changed our classical planning view of the world and instead allow ourselves to put rewards on goals and also allow ourselves to choose between the goals. So which goals should we actually achieve and which shouldn't we? So goals have utility, and they have utility or cost interactions, and also goals may have deadlines, so we might be able to achieve a goal, but we might achieve it late and get some penalty for achieving the goal late. Actions have different costs, so there's costs involved. And our goal in this view of planning is to find a plan with the highest net benefit. That is, the highest cumulative utility, or rewards we get for all of our goal achievements, minus the cost for actually achieving those goals. So these kinds of problems are all over the place, and in fact humans usually when they're planning will have partial satisfaction planning all the time. They'll have to deal with the fact that they can't actually achieve some goals, or they have to achieve them late and get some penalty for achieving them late. But they're also in many applications, so they're ubiquitous in the Mars rovers domains, UAV domains, logistics domains, and the reason why we might not be able to achieve goals or achieve goals late often is because of both logical constraints and resource constraints. So, and there could be a variety of reasons why we don't want to achieve goals or cannot achieve goals. So one question is, why is this, I mean, since humans have these kinds of problems all over the place, why haven't we really looked at these problems much before? And one reason for that is that planning in at least the last dozen years has just recently had sort of a big boom in the ability to scale in terms of how fast we can find plans. So before, about a dozen years ago or so, we were only able to find plans of 6 to 10 actions in minutes. Now we're able to find plans much more quickly, and much longer plans much more quickly. And so now we're able to encode part of the Munich airport and actually find plans for scheduling planes in the Munich airport.
But you can't find your way to the gates. You know it well.
That's it. So the scalability enabled us to look at different different kinds of system dynamics. So we could look at planning problems that involve numbers, temporal planning problems, metric temporal, so numbers in time, partial observability problems where we don't know everything about the world, and also stochastic planning problems where we have probabilities. So this enabled us to look at this dimension, but we can also look at stuff that's more like PSP, where we are actually trying to find cheapest plans, highest net benefit plans. Now that we're able to scale, we're able to also look at more complicated optimization metrics. So that's kind of where my work falls. So I'm going to relatively quickly go over some of the work that I presented for my proposal. I'll start with going over a quick history of partial satisfaction planning, including my work in it. And then I'll talk about partial satisfaction planning in general and goal utility dependencies, so dependencies between goals, getting different rewards dependent upon which set of goals you achieve. And also I'll talk about a study of compilation methods in terms of compiling partial satisfaction problems into different kinds of problems. And then I'll talk about the completed proposed work that I did that got a Best Student Paper Award at ICAPS this year on time-dependent goals, so actually getting penalty for being late on for achieving a goal.
Did you submit that on time?
I got 0 costs for that. Okay, so just an abbreviated timeline of partial satisfaction planning. Really, people have known that you can't achieve all goals for a long time. But in terms of solving these problems technically in AI, there's been sort of sparse discussions about this. This is just an abbreviated timeline. Other people have talked about the problem at various levels, or at least mentioned it. Herbert Simon discussed the possibility of not achieving goals that you have from an organizational point of view. Feldman and Sproul talked about it in a decision theory point of view, and Hadaway and Hanks talked about it in a way that it more closely resembles what we are looking at in terms of partial satisfaction planning. Dave Smith, who's with us today, then gave a talk in 2003 and wrote a paper in 2004 on it, and then after that there was a big explosion in research in the area of partially satisfying goals. And I was a big part of that. This is all my work. This is before Benton and after Benton. So this is a section of my work that I've done in the area. As Ram mentioned, I gave a tutorial at AAAI on it in 2010. and subsequently have done research.
Did other people also publish that?
Yeah, there is other work on also at the time. Yeah. So as I said, I got the Best Student Paper Award here, and back in 2006, I was able to get a Distinguished Performance Award, which is sort of like second place in using a planner that we developed called GeoGMPS. So I'll go ahead and talk about PSP and utility dependencies. So just to ground the problem a bit. Here we have a Mars rover's problem, where we have a rover that needs to collect goals at different locations. So at location alpha, it has a soil sample it needs to collect, or it's asked to collect. At beta, a rock sample, and at gamma, image. So each of these goals is given reward, and then each of the actions moving between locations and collecting the samples each has a cost. And the objective here is to maximize our net benefit, our reward minus our cost. So that's just sort of the basic level where we give rewards to each individual goal. But you can also consider giving rewards to sets of goals. So here we have a goal G1 that has a reward of 15, a goal G2 that has a reward of 15, and then if we get both together, we'll get extra reward of 20. So we can define functions over each of these goal sets that we care about and get a complete, and then when we get these goals, we can ask our utility function that we've defined exactly how much reward we get. So in this case, if we collect all, we'll get 50. And these values for these sets of goals can be either negative or positive. In this example, I have extra positive.
But doesn't the lottery work that way?
The lottery?
You get some of the numbers, you get all the numbers.
So one way you can consider solving these goals is actually by trying to find a plan, or solving these problems is trying to find a plan for each goal set. So I can find a plan for just alpha, just beta, just gamma, alpha, beta, alpha, gamma, and just all of the sets. And our little toy problem we have here, that would give us 8 possible plans that we would want to find. That's including the null plan, which is no plan. But this, of course, becomes very impractical very quickly. As I get more and more goals, then I have to get more and more plans, and planning takes time, so we don't actually want to use this approach. So finding a plan for each goal set is just too slow. So instead, what we tried to do is first we began looking at an integer program formulation, because integer programs are designed for optimization, so it seemed to make sense. There are a few issues that we already knew about when we were doing this, and that one of them is that integer programs are what's called bounded length optimal. So that means that if I find an optimal solution for 30 steps, there may be still a better solution at 40 steps. So I could actually increase the number of steps that I'm allowed in my integer program and get a better solution.
Clarification?
Yes.
So casting this as an optimization task doesn't mean you are trying to find an optimal solution. Are you?
In this case, we asked it to give us an optimal, but we did allow it to output. It has an anytime sort of search, so it allowed us to output subsequently better.
So in the limit, it will find the optimal. Within
the limit, it will.
But realistically, it may not. That's okay.
That's okay.
Right.
Yes. Yeah, so that's one issue. The other issue is simply that it's kind of a slow approach. It didn't do as well as the approach that we ended up with, which was doing a heuristic search. So we modified a heuristic search planner that used sort of state-of-the-art heuristic search methods, and we changed the search methodology a bit, and also generated a suite of heuristics just for solving this problem. So the idea with one set of our heuristics is that in the first step, so this again is our heuristics, not actually solving the problem, but our heuristics in the search. So we try to find a lowest cost relaxed plan for a relaxed version of the problem. The problem relaxation is we ignore all deletes. What that means is that, as an example, if I'm at location A, and I move to location B. In the real planning problem, I would delete the fact I'm in location A. In the relaxed problem, it's as if I'm in both places at once, at location A and location B. So we solve a relaxed version of the problem. This is an estimate of the lowest cost. It's not actually the lowest cost. Then we build a tree of the cost dependencies. What that means is if I have an action that leads me to finding the solution to two goals, then this action has a cost dependency for those two goals. And then we optimize this relaxed plan by various methods, and I'll talk about those.
There is always a relaxed plan that achieves all the goals?
If there is not, then there's no solution. At least none in the search at that point. Okay, so this is what we end up building in order to solve the relaxed plan. This is called a solve for the relaxed plan. This is called a relaxed planning graph. Just very quickly, we take our initial state and we apply all of the actions that we can apply at that initial state, and then we get all the facts from applying those actions. This again is ignoring delete lists. And then we do the same here with our new state, and we apply all of the actions that are applicable there until we get to a point called level off, which means that we can't, the next step that we go, we get a repeat of our previous step. I've cut out that last part where it's a repeat. And then we also propagate the costs. So we look at how much it costs in order to reach each of these goals by taking the cost for one action, giving the cost for that action to the propositions, and then on the next level adding that cost to the next actions and so forth until we get a cost estimate. And that gives us one kind of heuristic that we call H-sum, but that heuristic does not extract a relaxed plan. So when we do extract a relaxed plan, we get a different heuristic that we call H-relax, and what this allows us to do is give slightly better estimates on the actual cost for achieving each of these goals. So we actually trace through and see how much it costs to achieve each of these goals, given the current actions in the relaxed solution. And then we have, for each of these goals, a reward. And given our rewards that we have in the simplest case in the planner SAPA PS, given each of the rewards that we have, then we can take away negative rewards from this. So we take the net benefit of each individual goal and subtract ones that look like they're going to give us negative reward. So then we have our final heuristic value. And this is just the simplest case of having individual rewards, not goal utility dependencies. When we do goal utility dependencies, what we do is we encode this entire relaxed plan that we've extracted and the cost dependencies as an IP, and this IP allows us to encode the goal utility dependencies as well, so then we can prune away what looks bad based upon our IP solution, and then we have a final heuristic value. And we call this heuristic H-guy relax. And we implemented this in a planner called Spuds, which is important in one of the results slides. The other thing that we did was we realized that what we need to do is think about not just goal selection, but also action selection sort of simultaneously. The previous approach had multiple steps that we went through. What we wanted to do is think about both action selection and goal selection simultaneously. So what we decided is that we can actually create a heuristic that encoded both of these things. And what we did is we took a compact encoding of the original planning problem using what are called multi-value fluents. So we compiled the original planning problem down to a multi-value representation. What this means is that if I have a truck at a particular location, and I move to location 2, so from location 1 to location 2, I actually will know that I've deleted the fact that I am now in location 2. So this gives us more mutual exclusion information. The nice thing about this encoding is rather than relaxing the delete list, it just relaxes action order. So I have an idea of what actions that I need to execute, but I don't have a really good idea of what order that they should be executed in the original problem, which is fine from a heuristic standpoint because all we need is a value. So this generates an admissible heuristic.
No, if you do want a good value.
What's that?
You could make up a number.
Well, that's true. It gives us a pretty good value. Yeah. So this gives us an admissible heuristic, which is nice because what this means is that if we use this heuristic and we search and our search stops, then we'll have an optimal solution. But again, as we're searching, we can output better and better solutions over time. So just a quick overview of what this heuristic looks like. It encodes the planning problem by seeing if an action executes, then all the effects and what are called prevail conditions also must be true. These are like preconditions. If a fact is deleted, then if you want to re-achieve that fact, you must re-add it. And there are encodings also of our goal utility dependencies. This is just an overview of what our constraints look like and the variables. What we also did on top of this is we realized that sometimes part of the relaxed plan is actually executable. In fact, other people have sort of realized this too and used a similar method. So what we did is we took relaxed solutions and then we used a look-ahead on those relaxed solutions, meaning we tried to simulate the execution of as many of the actions as possible to get us deeper into the search space. This helped us collect goals along the way, which is a nice quality. So some of the relaxed solution actually might collect some goals and give us better and better solutions. So what we found with this heuristic, the last one I just discussed, which on here is HLP, is that when we're trying to find optimal solutions, we found 15 optimal solutions in the problems that we generated. We generated 60 problems in a rover's domain, a Mars rover's domain, a satellite domain, and a xenotravel domain, which has to do with delivering people to their various locations using airplanes. It's a logistics type domain. We were able to find 15 optimal solutions versus our strawman approach that we used called HCHI Max, which only found 2 optimal solutions. And also, when we were using the look-ahead, we found that it actually did better than our inadmissible heuristic that used the relaxed planning graph that I talked about previously. So this seemed to be, at least in these domains, the superior approach. The other thing that we tried to do is use learning to help our search. So what's interesting is that each state in a partial satisfaction planning problem, if all goals are soft, then every single state is a solution, meaning that there are actually no hard constraints in terms of which goals that I need to achieve. So there are no hard goals when all goals are soft. So each state I'm in, even doing nothing, is a solution in that case. What is nice about that is it allows us to give an interesting estimate on the value, the G value that is in search terminology of each state in our search. So we looked at methods of perhaps using this in order to help us learn heuristic functions. What we found is this algorithm called STAGE by Boyan and Moore. It was originally used for just general optimization problems, and one issue with it, though, is that it was using handcrafted features. So for each problem that they were solving, they handcrafted each of the features for that problem. But in automated planning, we like to be domain independent, so we had to automatically generate our features. So we tried 2 things. We tried something called a taxonomic syntax, which talks about the relationships between propositions. And and also we tried a propositional set of features, so basically just looking at the entire state, what's true and what's not. Using this, we generate a star search. We go to some n number of nodes. Using the tree that we find, we generate a value function. Using this value function, we do a hill climbing search, meaning we look for the next best state at each state. We look for the next best state based upon our value function, and then we find a new restarting point and restart our O search from that point. So now I'll discuss the compilation methods that we studied.
I have a few questions.
Yes, yeah.
That's a good, just to clarify.
Yeah.
So what is a goal here?
What is a goal? It's a proposition. So a single goal would be a proposition, but I also allow for goal utility dependencies.
Okay, so single goal is a proposition.
Yeah, yeah.
And so a set of goals when you're given is a set of propositions.
That's right. Yeah.
Okay, so what if you want to have a set of goals where something has to be false?
Well, you can compile out that in
So
at least
you
in
have
the
to compile
strips. Yeah, but
So
right
what do you
now that's
compile
true. What that means is that I basically, if I have a goal that says not something,
Right, I want it to
Yeah.
be false.
yeah.
With variables in it?
What's that?
With variables in it?
No,
So
not
that
variables.
So the negation with universally quantified variables?
No, something
No.
not false there, not on the table.
Yeah, just propositions.
Yeah, but not,
not-
how about nothing on, there's nothing on this.
Yeah, I don't
Okay.
handle that at all. Yeah.
But simple not.
Yeah, so simple not is so in our actions, if something is negated, then, well, first of all, I create a new proposition called not this thing. Just create a proposition called that.
Okay.
And then whenever something is negated in an action, then I negate the original proposition and then make true the thing that says not.
So you just add this new thing and then go
That's
to the
right.
whole action.
That's sort of the easy way, but right now I don't directly handle it. Of course, it's possible to modify this directly.
Okay, then just
Yes. Okay, so I'll go ahead and talk about the compilation methods. I just have a couple slides on that. So for partial satisfaction planning, as I said, there was kind of a boom in studying the problem around 2005, 2006. And in fact, in the planning competition in 2006, there was developed a language called PDDL3, and it allowed for soft goals. There's a slight difference in that and in their representation. And what we were using is if you achieve a goal, then you get reward for it. What they were saying is if you don't achieve a goal, then you get CASA for it. It's a very sort of straightforward thing where you just want to make a minimization into a maximization. So we can compile these kinds of problems into our version and solve them. In fact, we did that in the competition in our planner, Yochen PS. The other thing it turns out you can do, and in fact you could do from either of these languages, is you could actually turn the entire planning problem into a cost-based planning problem, which means that rather than trying to either maximize our net benefit or minimize the number of violations of goals that we have, we actually now can just try to minimize the cost of actions and totally ignore any costs or rewards associated with goals. So we were curious at which one of these approaches, do it directly handling partial satisfaction plannings or actually compiling it into a cost-based planning problem, which would do better. And this is just a quick overview of how the compilations work. For compiling violations into reward, it's a pretty straightforward thing where you just use one action. It's a little more complicated to compile out, but not much more complicated. To compile out violation costs into actions, you need 2 actions instead of 1. And so we were then just ran both approaches to see what happened. It turned out, at least on our planner, that Yochen PS, the planner we had, did better, and this is where we're handling the partial satisfaction planning problem directly, than Yochen COS, which is trying to minimize number of actions. In some domains, it just did much, much better in a couple instances. In other domains, we did a lot better in more instances. and in some domains we did about equal. So now the more recent work, handling time-dependent goals, and this is again where we get some, if we're late for achieving a goal, then we get some penalty for that. So if we look at, in terms of the previous slide where I talked about system dynamics versus optimization, so we have different system dynamics in temporal planning, and Will can tell you that there's a lot of intricacies here. But just for the sake of our discussion, we'll have temporally simple versus temporally expressive domains. So temporally simple domains are where you can just use the classical planner to solve them effectively and then reschedule the actions temporally as if with the times back in, and temporally expressive domains is where concurrency is required in order to solve them. And so what we ended up doing is generating a planner that can handle discrete cost deadlines. So that's deadlines where if I'm late for something, then I pay a full penalty for it, for being late. And also continuous cost deadlines on both of these, so we can handle both temporally simple, temporally expressive. Continuous cost deadlines are where you progressively get more and more penalty for being more and more late. So we can ground this into a problem where we'll have the dilemma of the perishable food, and I talked about this example in my proposal talk as well, where we have different produce that goes bad after a certain number of days, and we must deliver it to different locations. So we have to deliver apples to alpha, blueberries to beta, and oranges to gamma, and we get some penalty if we're late. And we can look at this in terms of shelf life. So what we really want to do is maximize our profit, and but to do that, we want to have the most shelf life for these items. So if we just assume that our cost starts right away, then the minimum make span plan, which is actually going from alpha to beta to gamma, gives us a shelf life of 13, and all of that comes from apples, it turns out. If we have a slightly longer make span plan in terms of number of days, then we get longer shelf life. And it turns out this plan also distributes it much better.
Are these genetically modified?
I looked up.
You didn't use genetic algorithms. No.
I looked up the just to say I looked up these values, and they were just for organic, actually, apples, oranges, and blueberries.
So basically, you could avoid planning if you just put some fertilizers and
Right.
some artificial
Right. So how do we handle these problems? We can consider two approaches. So I should mention, which I just realized, I'm not sure I put this on the slide, is we modified a planner called POP-F2, which is a planner by Andrew Coles and Amanda Coles at King's College in London, in order to solve these problems, versus the previous approaches, which were modifying a different planner. So at any rate, we could handle continuous costs in two different ways. We could either try to directly model the continuous costs and solve the problem, or we can try to compile our continuous values into discretized cost functions. And we do that by having a small little subset of a language called PDO3, which I talked about before, which does allow you to specify deadlines and have full cost for not achieving them.
You were just saying that you were looking at two different problems, one with continuous costs and one with discrete costs?
Well, we have the planner capable of, we implemented a planner capable of handling both.
But were you separately studying problems that had discrete costs, or you just have two methods for one problem?
Andrew and Amanda had implemented the ability to handle discrete costs, yes. And that was totally them. So I did not personally look at that, and I implemented the continuous cost stuff.
Is there any interesting difference between using the discretization on the continuous costs and handling a problem which is just inherently discrete costs? Would heuristics differ?
Yes. So after the work was published, we had a long discussion about that, and in fact, in the planner, yes, but actually no. we end up handling discrete costs differently than we handle continuous costs. But then I've actually emailed them and I said, why are we doing this? And so it turns out you don't have to, and it's not really clear whether their method or the other method would do.
So that's future work to look
That's
at that?
basically, yes, we have to look at that.
So the main motivation that even try to compile into discretized costs is because their planner can...
No. It's because I was very curious whether, in fact, it's from discussions with the group, whether just because I have a continuous model doesn't mean that I have to actually solve the problem using that continuous model. I can discretize it. And it seems to make more sense to have a discretized function in some ways for planners. And I'll talk about that a little bit, is where you get the benefits here. So one thing it's a very technical issue, but one thing we had to deal with was the fact that PDL 2.1 and all subsequent versions of PDL, the language that we were using to model the domains, doesn't handle grabbing the current time point. So when an action begins, I don't know the time at which that action begins. So what we ended up doing, there's a couple things we could have done, but what we ended up doing is modeling a small portion of a language called PDL+, which allows you to actually specify time, and you can actually grab the current time that an action begins or ends. So in order to directly model continuous costs, it ended up being not all that bad. So what we ended up doing is we created a new goal called collected, in this example, collected having apples at location alpha. And then we have an action that has the precondition of having the apples, and then given at alpha, and then given the current time point at which that goal was achieved, we can say exactly how much extra cost we want to add to our total cost function. So in this case, before this deadline, we get a value of 0. In between this deadline and this point where we get maximum value, we have a linear function here, and after that time point, we get a maximum. So we do this using a conditional effect.
TG is a multiplication?
I'm sorry?
TG is a multiplication? T times
No,
something?
no, I'm sorry. That should be on subscript. Time that the goal was achieved, TG. So for our search procedure, we used pretty much the same search as used in the original planner F2. We find an initial incumbent solution using a search called enforced hill climbing, and then, excuse me, then after we find an incumbent solution, if we exhaust our space and can't find one, or after we find one, then we restart our search using a best first branch and bound search.
Why is it called an incumbent solution?
An incumbent solution, that's just the common terminology for the first solution that you find. So I know.
Okay.
It's already there.
Well, sure, but so is the next one.
Yeah.
Okay.
And so then we use the solutions that we find to prune our search space, and we have an admissible heuristic on our cost value that we can use for pruning our search space. So just to show how we discretize the costs, so that's how we solve the continuous case. To discretize the cost function, we take our original cost function and we split it up into several deadlines over the same goal. And then given these new deadline goals, we just can sum them up. So if we're late, then we get a value based upon when we actually achieve the goal.
I'm sorry, why is it useful to discretize?
Well, we thought it would be useful because people that have done that have shown progress.
Okay.
Yeah. So the question is, so we have a discretization, and one question with this is what is the best granularity, and we studied that in our results. But we also found that discretization has some advantages and disadvantages that we try to exploit later. it turns out that if you find a first solution, so this is just a simple cost function on, say, just one goal. If we find this first solution that's here, then this solution looks equivalent. So this solution will actually be pruned away from the search space, and it reduces the amount of search effort that you have to do. And in fact, using our admissible heuristic, we can reduce that search effort relatively early, and we won't try to find solutions that are on the same cost plateau. And the issue, of course, is that we'll miss this better plan. So while we're reducing our search efforts for finding solutions, we're actually also missing our better plan. But there's an advantage to that too. This solution looks better. So a solution here would look better than these two solutions. So what this does, it allows us to make jumps in our search space to finding even better plans than our previous ones. So basically what we have here is we have a continuous representation of the problem, where we have more accurate solutions that actually represent the cost functions that we have. In the discretized version, we have a faster search, and it will look for jumps in quality more quickly. So what we thought of is how can we merge these benefits that we have. So what we came up with was something called tiered search. And what tiered search is it mimics the pruning capabilities of discretized search. So after I find a first solution, in this example I find a solution of 128, in my next search, so first I should say, each of these searches happens for 5 minutes, or until search space is exhausted. So I'll find a solution of 128, I'll continue to search for 5 minutes. If I find no better solution, then I'll switch to another search. And in my next search, I'll take my current solution and then prune everything between 64 and 128. So basically, or actually anything that's greater than 64, I should say. So all solutions that are greater than 64, I'll actually prune away. So this is helping me look for bigger jumps in solution quality. And then I'll do this for 5 minutes, and then flip to anything less than 96, and so forth until I do this 5 times and am searching again on the original continuous representation. So we implemented this search and tried it on 3 different domains that we generated based upon the International Planning Competition domains, 3 International Planning Competition domains. We developed an elevators domain. In this domain, the idea is people get impatient, and so there will be penalties for not getting them to their location on time. The goals were generated such that they assume that they'll be able to immediately enter the elevator.
This is why it goes up and down?
It's mostly going down.
Yeah, it's mostly they assume that they'll immediately be able to have the elevator open and they'll be able to get to their floor immediately. So their cost function begins if they don't get to their floor right when the plant starts. Or not right when the plant starts, but if they're not able to get into the elevator right when the plant starts. So we tried various ways of discretizing the problem. We tried the continuous approach and the continuous tiered approach that I talked about. But as sort of a strawman approach, which actually did well in this domain, we also tried to just minimize makespan. So it turned out minimizing makespan in this domain did pretty much as well as our tiered approach. It's just you take the aggregate between them. But in terms of discretize, it's very hard to see which one of these does better. But it's clear that discretizing isn't always best, because in at least discretizing into 3 parts and 5 parts, we don't do as well in many cases.
Okay.
Yes.
So why did you create this domain instead of using a variation that existing domain? Is there any particular structure about this domain that?
It seemed to make sense as a domain where people would not want to be laid at, I think, is why we chose this domain. we were looking at, I wanted to have a variety of domain structures. So my point in choosing domains is, okay, we'll have one that's kind of logistics, one that's kind of manufacturing, and then crew planning, which is more of a scheduling thing. So we also tried crew planning. Crew planning is basically planning a crew schedule on the International Space Station, and you have, in this case, deadlines of when people should go to sleep. So if they're late on going to sleep, then they get some penalty. And you also have deadlines on delivering payloads. So we tried all of our approaches. It turned out that our continuous tiered approach did much, much, much better overall than our other approaches that we tried. Minimizing make span, interestingly, did do well in some of the problems, but it did terribly in some of the others. And the one where minimizing make span really didn't do well is in the OpenStax domain, which is a manufacturing-like domain. And that domain, we just assume the orders will be pretty much ready immediately, so the cost function starts immediately, which I guess it kind of makes sense because we had also different gradients on our deadline. Minimizing make span didn't do as well in this domain, and in fact, really the continuous tiered approach is the one who, at least in the aggregate, looks like it did the best.
Am I reading that correctly, that the minimizing make span did essentially equivalently to the continuous approach?
No. So minimizing make span is here, and continuous approach here.
Do you have the sense of how close the best solution among all the approach to the absolute optimal solution?
No, we don't have the optimal solutions.
So assume that you just run brute force for small problem for a few hours. And it give you some indications of how close it can be, like, I don't know, very close, or can be very bad. We don't know.
It's true. I mean, since these are domains that I've generated, then there's no one else has really played with these domains except for us right now. So at least as far as the deadlines that we're generating.
So I just wonder, is there any way that run the brute force search?
I think so.
For a very small problem for
Sure.
a few hours.
Sure.
Or smallest problem in each domain.
I mean, that's certainly something that we could try, or we could try and see what happens. But
because it's really hard to.
It's always hard when
see.
you're doing satisficing. I mean,
See, this graph, it looks like that one is really the best. But
so
Patrick
Patrick Hoslam this year had a paper on just this topic, right? In finding better and better lower bounds, so that you can get better guesses as to how good your solutions are. So, okay. Even though we started late, I'm on time. Somehow. So, partial satisfaction planning, just to summarize, is ubiquitous. We all have to deal with it. It foregrounds quality, which is an important thing that hasn't really been looked at all that much in terms of finding satisfying solutions. Although just now, I think people are starting to get in the mode of really thinking about that. In 2008, for instance, the planning competition foregrounds quality. And of course, it's present in many, many applications, which goes along with the fact that it's ubiquitous in human life. So some of the challenges that we're faced is in modeling the partial satisfaction planning problems. So in terms of what is the best way to model, for instance, goal utility dependencies, and what we used was something that was quite general, but there are other possibilities as well to model dependencies. For instance, there's things called CP nets that are potentially good for modeling these things and maybe more apt to human users, where you just model the dependencies in more of a tree fashion. Actually, they would be called UCP nets with utility. And also how you model these soft deadlines in terms of solving methods. So is it best to model them using the continuous or the discretized version? And as well, there are many other issues to deal with modeling cost deadlines. For instance, time windows are important, but we didn't go into those. So some things that I've looked at along the lines of looking at PSP, I have another Best Student Paper Award with Jordan Thayer that's at SOX this year, which is a combinatorial search conference. Also looked at partial satisfaction planning in some sense for deadlines, for online problems, and also human-robot teaming, and some issues with search as well, which go along with this paper here, on the issues that you deal with when you're looking at variable cost search problems. So some ongoing work. I'm talking actively and probably going to start work in the next couple months with Andrew and Amanda Coles on handling non-monotonic costs, in particular looking at quadratic functions, looking at time windows, that is after the cost function goes up and then back down.
Sorry, why are non-monetized costs a problem at all? Why does your framework already handle it?
Because of basically scheduling. It's easier when you know that earlier is better, because if you're having monotonically increasing costs, then earlier is always better in terms of achieving a goal.
And that's built into your search algorithm, or just
it's built into the scheduling part of it. So when we reschedule the actions.
But the I'm sorry, but the non-temporal aspect of your system does handle non-monotonic. Oh no, there's no continuity.
There's no
Okay, never mind.
So the other thing we want to look at, and this goes along with non-monotonic costs, are time windows. And also, we're excited about the idea of starting cost functions after certain facts become true. So this would be like axiom-based cost functions, where if certain formulas become true, then a cost function begins.
Oh, you could call them open world quantified cost functions.
Obviously, like this here.
Sorry, that was a dig.
No, I want to patent it.
Is that motivated by their work with this repositioning?
Yes.
So this is actually like motivated by super real world
This
problems?
is motivated by fleet repositioning problem that they're working on in King's College. That is this goal achievement based cost function stuff.
Is that the other stuff too?
Well, I don't think so. But I mean, this stuff is good. I mean, I see an application here for their fleet repositioning issues, but I think this is more broadly applicable to satellites and things like that. Although I just haven't thought about it. I just started talking to them about this at ICAPS, which was only 3 weeks ago.
Were they called fleets because they were fast? They might have been. I'm sorry.
These are ocean liners. They take weeks to sail across the Pacific.
Yeah, but in the old days, they might have been considered fast.
The other thing that we're starting to talk about is handling in fact, actually, we've talked about it quite extensively, even in the last couple of years, multi-objective planning problems where you have costs of different sorts. So costs involving fuel, costs involving money, and so forth. So you have multiple resources, and this goes along with finding Pareto sets of solutions, which Schwan talked about earlier this morning, and just handling various plan quality measures with them.
And why? I mean, since you always have to make a decision, why is that ever desirable?
Because you can go through an iterative process where you allow people to decide if you prefer using less fuel this time or prefer using less money this time. You allow the user to choose.
Okay.
Yeah.
But then they get to determine the weights, and they
They
don't
effectively determine
and
the
they
weights.
don't have to do it explicitly.
Yes, all right. That's the idea. The other thing I should mention here is also resource constraint planning, which is really something that is very important, where you want to find solutions to planning problems where you actually have just constraints on the amount of resource that you can use in general. So here are a list of references. All of these are all the references are in my dissertation. But these are particularly applicable to what I just talked about in the talk. And thanks very much.
So the floor is open for public questions. Anybody can ask questions?
You want to work on continuous goals, like metric goals, like you have to achieve skill level higher or something. You need to achieve less than that. It seems to fit very well with the continuous.
That's a good point. I've given some. I mean, there's a lot of work since the stuff I did in 2005 on handling continuous metric values, and in fact, Andrew and Amanda had a lot to do with that work. And I think a lot of the stuff that they do is applicable to that problem.
It seems to fit very well with linear increase or quadratic increase.
Yeah, I think so.
Benefit.
Yeah.
Based on the level that you achieve from that.
Right. And basically, I think what you would be doing is changing their LP. They have an LP for how they solve these problems.
Other questions?
Wait, you mean?
No, other open questions, and then then it will be closed session with just the committee. Going once, going twice. Sold. Okay. Sold to the public, not to the committee yet. Okay. So you can stop that.